Alright guys, good morning and welcome to the stream. We are back with another iGEM Munich software development stream. As you guys know, we've been doing this for quite a few days now. The idea of this software is to make it easy for anybody who has even the slightest inclination of doing custom receptor stuff, intracellular stuff based on biomarker concentrations outside of the cell, whatever you want basically, using the so-called MESA receptor, which we can see here, MESA receptor. Pretty easy, actually. Yeah, I think this very first one describes it. It's basically a custom receptor that you can build yourself, or you use an existing dual binder system, which you can have this intracellularly or bound to a membrane. We're going to look at the membrane version right here. Basically, if this blue biomarker binds these two halves, they come together outside of the cell. This causes the inside of the cell to also dimerize, or well, this entire construct to dimerize, of course, right? And then this protease here can cut the protease recognition sequence, this purple part, which releases the yellow cargo intracellularly, and that can cause whatever. You can build AND gates, whatever you want. And so this is a really, really powerful tool, and we're building a software that can make it easy for anybody to use this. We've already come pretty far. There are only a few more things that we want to do, but the core functionality has been implemented for quite some time now. However, there's always additions you can make, and if we want to win iGEM software special prize, which we very much want to do that, then we have to abide by these judging guidelines right here. And if you look down here, I think it's page 83, we can see the requirements for software tool, which have actually been updated this year. And I think the software tool aspects are pretty well, outlined pretty well down here. You need to be compatible with other software or data formats, which we very much are this. All the downloads and all the exports, also from the Python package, which we'll get to in a bit, are in GenBank format, which GenBank is just like annotated sequence essentially, but also if you use a software that can work with GenBank files, you can do a whole bunch of stuff right there. And so that's really important. It's good that we got that covered, because that just makes it so much easier to work with this. If you had FASTA downloads, yes, that would be also fine, I guess, and you could manually annotate it maybe, but just using GenBank makes this a lot more compatible with existing software and existing workflows in synthetic biology. Second point, was this software validated by experimental work? Not yet. Not as of now. We have a construct in the working, but there is an issue with how many nucleotides we get sponsored. So yeah, we'll have to see what exactly this will be, because there might be a 3-step or there might be a 2-step process. We can get into that later if you'd like. But for now, we are going to focus on continuing to develop this stuff. However, if we get to it later, either today or maybe tomorrow, we can also look at some other targets that might be of use and that might be considered for this experimental work. Right now we're looking at progesterone, as you maybe have seen in our video, in our competition video submission. We are using progesterone for like fertility reasons, and that is a really interesting target. The thing is, does it work? We don't know that yet. In our simulations, it's looking fine. We can also get into that in the next few days when we do software and also dry lab streams, where we will show you guys how to work with the stuff that we've worked with over the past few months in this year's iGEM competition. Which that's going to be that's supposed to be a great deep dive and also overview of the different tools that you might use if you're a future iGEM team. How well can the software be integrated? Point 4. So we have an API. This API is capable of doing everything that the GUI tool is, except it can do a bit more. Same thing goes for the package. Yesterday we started this. I just before the stream started, I uploaded a package to PyPy. So if we go check that out, this is basically the first version of the Mesa Designer package. Oh, look, it still has the wrong description. Very nice. Yeah, anyway, very small package right now. We still have bit of stuff to do, but it can already do the core functionality stuff. So right now you can build your Mesa in a very intuitive way, in my opinion, and then you can get an output in GenBank file format, whatever you want. Yeah. I guess we wanna do some adjustments on the README, etc. and description. Okay, going back to this again. Yeah, okay, that's fine. Is the software user friendly? Personally, I think so. However, we're gonna make the videos to guide you through the process. We're gonna make the documentation very clear, very detailed, with good examples as well. This goes for the API, the package, and the actual GUI software, which transitions nicely into how well is the software written and documented for future groups to extend and improve. Right. This is Python code, so inherently it can be very easy to read. I think this definitely goes for the Python package. This has been constructed with future extendability in mind. The software itself and the API, same thing. So especially the API, it's just a bunch of endpoints, right? You know how an API is usually structured, and it's very clear what everything does. There's automatic integration with OpenAPI documentation. So yeah, that's also covered. For the software itself, it's Streamlit, which is easy to work with, but the state management system isn't the most intuitive. Once you understand it, it's perfectly fine. It's very nice, and you can do a lot of powerful stuff. But it's a big beast, and you have to get your head around that once. So I guess there's some documentation, some code commenting that should be done in that regard. Performance evaluation, we've already covered this a few times now. We will go through the commits from beginning to end with the Mesa Designer package and just test how the performance has changed. I mean, we know already that we shrunk it down from 50 gigs to, or 55 gigs to like 500 megabytes, simply by removing a bunch of downloaded data that, you know, we can also pull in from RCSB. The delay is like 10 times the time it took to get it locally from disk, but you know, we're talking about 0.02 seconds versus 0.2 seconds, so it's perfectly fine. And I think making it a what would that be, like a 100 times smaller download is very nice. Yeah. Okay, then we have architecture diagram. Yep, we can also create that today if we get to that. Installation and execution scripts. Yeah, this is very much covered. I mean, with Python packages right now, it's absolutely amazing. We can just pip install Mesa Designer and you have the entire Python package. What is the plan for today? Let's see. I think I'm gonna start off by including a proper README in the Python package and maybe a good description as well. We can write some tests there, and we can create some more functionality, especially when it comes to getting an overview, getting sources. Potentially, you could also think about inclusion with other software packages such as Bindcraft or CollabFold. Yeah, I think that might be cool to have. Although, no, I don't think that makes that much sense, because especially Bindcraft setups can be very different. But we could definitely create a like compatible output kind of thing. So, for example, if you think about bolts, they have a very nicely structured YAML output file. So I think we could output to that, and then the user just has to pipe that into bolts. But then we don't have to have a fixed integration, so to speak. It's very flexible if we just give the necessary input to the next software, instead of trying to actually run that software in this tool, which is designed to design Mesa, not be everything, right? Yeah, let's do that. Okay, so I think we'll start off with, let's see. Let's get a proper README in here. Yeah, let's update this README to be like actually good. I will quickly show you be IDE. Okay. This is the README right now. Very nice README. So I think there are two things. First, we have to go into the TOML and update this. This is, so I guess we could just call this Mesa Designer Python package. I think, honestly, I think that's a fine description. Let me just quickly check Slack. We have something to talk about, I guess. See what they have. Oh, okay. Okay, there are a few different messages right now. Let's see. Some questions about how regularly we're streaming. The answer to that is pretty much every day, especially now in the final phase. Ooh, we have some wonderful tattoo designs. Let me point that out really quickly. If you, oh, we have a chat message. What's that message? One day I started, oh, dang it. I didn't hear the chat alert. That's pretty annoying. Let's see if we can't find that chat again. Oh, I'm so sorry. I didn't get to see your chat. So if you feel like reposting that message, that'd be great. I would love to interact with you people. Yeah, going back though, we have a competition going for our tattoo. So if you don't actually even know what our iGEM project is, let me just quickly show you. Open that up. Sorry, it's a bunch of authentication really quickly. Don't want that to leak. Perfect, okay. So this is our current wiki. It's very much still under development, but essentially what we're doing is we are creating a tattoo. Let's see, I think this is turned on, but it's turned off already. Okay, we are creating a tattoo of living cells, which you can tattoo into your skin, and they can be essentially repurposed for whatever you want. That's what the Mesa receptor is about. That's what we're building with this software. And they can measure the live concentrations of almost any biomarker in your bloodstream, and then give you a live readout of that biomarker by changing the color of the tattoo. The cells themselves, or well, they don't change color per se, they change their contrast. So essentially, you could say when the biomarker levels in your bloodstream are elevated, then the cells might become darker. If they're lower, they become, less dark. So I think, yeah, okay. A lot of this is not written yet. Let's see if there's stuff anywhere already. Okay, yeah, perfect. So we're using like a 3, although I'm wondering if there's if we can find this a good like overview over the whole thing, because there are some really nice pictures. I think we have them just on our YouTube channel. So let's check that out. Yeah, perfect. This right here. So let's just mute that. If we go to this right here. Okay, so yeah, this shows it, right? You'd have the cells in your skin, and then through the bloodstream, the biomarker can be brought to the cell, and upon binding, they change their shade. How does this work? We are essentially using encapsulants, and encapsulants are really cool in my opinion. If we look at them on, yeah, okay, Wikipedia works. It's just a huge cage of proteins, and you can essentially, yeah, just capture stuff inside these cages. We are modifying these cages with tyrosinases on the inside. Tyrosinase is an enzyme which turns tyrosine through a 3-step process, okay, or 2-step process, into melanin. So the stuff that makes your skin dark. And we have these inside the encapsulant cages, and so if we can get a lot of tyrosine in there, they can become really, really dark. Now, if this was all there is, the cells would just be dark all the time, because there would be a bunch of encapsulants in the cell floating around, all being dark. However, we are using agglomeration domains on the outside of these encapsulants to agglomerate, like pull together all the encapsulants when the biomarker concentration outside, or whatever you want to measure, is low. And when it increases and we want the cell to become dark, these agglomerated encapsulants spread out through the cell, thus making the entire cell dark instead of a very small spot. That's the theory, and that's how this is supposed to work. So yeah, that's our project. For anybody who didn't know already. So yeah, you should definitely check out this video. It's a very, very nice explanation. And the key part that the software is supposed to work with is this MESA receptor, which just has these extracellular domains. Or if you're using intracellular, you can also do intracellular MESA, but we're doing extracellular MESA. Obviously, we want to measure outside concentrations in your body, in your bloodstream. And so whenever a biomarker binds these 2 domains, these chains will dimerize, causing this. There are 2 versions. You can use a split tyrosinase, where the enzyme is genuinely just split into 2 chains instead of 1. When these come together, they reconstitute in such a way that the enzyme functions. We also did a lot of work on that, and we will show you that in the next few days with our dry lab streams. If we continue here, you can see, yeah, it dimerizes, and then it can cut some target, and this animation here is pretty much just to show you it can bind whatever you want. You can create MESA in any way you want by just creating a new binder. We also did that with Bindcraft, which is again something we will show you throughout the next few days. That's pretty much this part. And so for this purpose right now, we're running a 2 competition. So if you have an idea and you would like to share your idea with us, please feel free to send it to us to our email address, team@igem-munich.com. I will also put that in the stream's description. Yeah, so if you have a design, if you have an idea, just scribble it really quickly and just put it on. Just send it to us via email. So if you want to see a design that already exists right now, we can't do that. Of course we can't, because Slack. Let's do it this way then. For example, this would be a very nice tattoo that somebody has designed. But feel free to be creative. Feel free to be, kind of. You can make joke tattoos. Maybe you'll win. We'll see. We already have a few submissions so far, but we'd love to get more. So yeah, feel free to participate. Okay, now going back to the actual Python package. Let's see here. So I don't actually know exactly how I want this README to be structured. So what we're going to do is we're just going to take a look at some other Python packages. Specifically, I think I'm going to take a look at BioPython, because they have not too unsimilar stuff. I guess that's a very convoluted way of saying that. But it's also, biology based. It's a fairly large package, obviously, but still fine. So yeah, let's see. Okay. I guess they have these things up here. It's fine. They have a nice logo. I think that's a good idea. So maybe just like iGEM Munich logo right there. Now I don't know how you include this right here, because I'm assuming you just add it to your source, and then you can just reference it in the README. Let's check out how they or where they keep this file. Does it have a name? It doesn't. Okay. Let's see. Raw master doc images logo. Okay. Or I guess you could. Yeah, but I was just not thinking you could base 64 encode it, but I don't think that's the best way to do it. Let's just see. Maybe there are some GitHub recommendations. Sure. Yeah, okay. Just relative path. Okay, nice. Then that's how we'll do it. 2. I think we're gonna put it in source. Yeah. Although, should it be part of the package? Yeah, why not? Yeah, absolutely. Can very much be in here. Call this img. Now I have to really quickly go and grab this file. Let me just find that. So that I'm just gonna take the logo that you guys also know from things such as the my background, etc. Our iGEM logo. Yeah, this one's good. Nice. If we go back to the IDE really quickly, we throw that in there. Okay. Yes, we want that. So yeah, this is just the iGEM Munich logo. Okay, so let's see if we can include this. Hello? Why won't you let me edit this file? What? Oh, I see. There we go. So I guess we iGEM Munich logo. And then we include the picture. What does this button right here do? Oh, awesome. That's pretty neat. So what we would want is in the designer package, source, images, this one. Yes, perfect. Okay. Doesn't like that. Yep, I can see why you don't like that. Let's do a relative path. Nice. Now, it's great that it has a background. Yeah, okay, let's just quickly make that transparent. Or we can actually, should we maybe take the dark version, like the black version instead? Let's see what that would look like. We have a very design focused day ahead of us today, because like I said, most of the package functionality is implemented. We can just, I guess, write a bunch of tests for that, but most of it works, which is really nice. I got to do all of that yesterday, but obviously it's more interesting for you, I guess, if we do some development as well, not just design stuff. But like, yeah, to be fully transparent, this is very much a lot of work of iGEM. So I'm unsure if the picture has the background or if this is just PyCharm being PyCharm. So no, wait, they're not transparent. Oh, okay. I guess it's probably the PNGs then that have the transparent background. That makes sense. Find those PNG. Yeah, perfect. Okay, we can grab both of these and take a look. Okay. Yeah, I don't think that's bad. Although it might be very very dark on here, so maybe the other one is better. Yeah. Yeah, the other one's probably better. Let's grab the dark.png, not black.png. This is probably a bit too dark. All right. Put that in there. Yes. Okay. Yeah. I mean, it's not great, but it's fine. It'll do for now. I mean, this BioPython logo honestly isn't too visible either. Let's just take a look at that. Okay. Yeah, just some information about BioPython. I guess that's not a bad idea. But let's move this to the top. Hashtag iGEM Munich. iGEM Munich is a TUM and LMU student club focused on participating in the iGEM competition, as well as outreach and public education. We can link to the iGEM Munich website. I think that would be nice. Actually, that's education. Find more information at. And then iGEM Munich. I think it's igem-munich.com. Very good. Okay. Nice. Yeah. And then I think we can include some information about the actual project. So Mesa Designer. The iGEM. Maybe it's a good idea to also link to the competition at iGEM Munich about our team, and or click here, and then we make the here a link to the official iGEM competition. It's just, I think that's igem.org. Yeah. Click here. For more information on the iGEM competition. All right, the iGEM Munich 2025 Mesa Designer project is a software package focused on easily designing, creating, and evaluating different Mesa constructs for any target. This package extends the functionality of the Mesa Designer platform, which we will link to. This is the GUI application. So I think we're just gonna link to the GitHub for this one. And its API. Okay, nice. Yeah, I think that makes sense. So let's keep going. Oh, they generate the documentation. Let's look at Sphinx. Sphinx documentation generation. Ah, so you still have to write it though. Yeah, okay. You still have to write it. Yeah, okay. So that might be something we can look into. Because I haven't really given thought to how I want to create the documentation for all of this. Obviously comments in the code, and some documentation on GitHub. For the actual Mesa Designer tool itself, for the GUI tool, I think the video is going to be a very, very good explanation, but not documentation for extending the software. So, yeah, I haven't really thought about that. That's maybe something we could look into for the impatient. Okay, I mean, yeah, sure. Why not? Just really quickly show off how you do it. I like that installation, but I don't think we're gonna call it that. Installation. Let me quickly check what it's actually called. So is it like Mesa Designer? Yeah, okay. The Mesa Designer Python package can be installed from PyPy using, and then we just have, I think we're going to do a double space and a new line, and then we can do here what backtick pip install Mesa Designer. I'm thinking if we should include a no, actually I'm going to put this here because there's still so much space over there. Start using this command. Easily installed. So a little bit more using this command. Okay, nice. The Mesa Designer package requires BioPython in order to function. Yeah, okay, sure. PyCharm hates it when you write in order to, just always wants to to work. And installs this as part of the installation process. Note: any additional requirements or dependencies of BioPython will also be installed. Okay, nice, yeah. Python requirements. I think we can make a separate requirement section. Requirements. Do we recommend a specific version? So I'm on 3.13, but I think we can just say, yeah, it should work down to 3.10, simply because, or I think 3.10, because I'm using a match statement in one of the files here. This match statement is, I think, was only introduced or properly introduced in 3.10. So, oh, you can only see the browser. Okay, well, let me just show you here. If we check out this repo in the source in Mesa, down here, we're using a match statement. And so I think this was only introduced in 3.10. So, when was Python match statement introduced? 3.10, yeah, okay. So yeah, anything above 3.10 right now. So let's add that to the README as well. And also let me show you the IDE again. Currently, any Python version above 3.10 is supported. Yeah, okay. I'm just thinking about how we want to write this. I think we're going to say, as part of its installation, Mesa Designer also installs BioPython and its dependencies. For more information on compatibility, check out BioPython. And then we just link to the BioPython. I think we can link to the BioPython PyPy entry. Okay, what else do they have in their README? Optional dependencies, installation from source. Yeah. We can add a contribution section. Contributing / bug reports. That makes sense. The synthetic biology and bioinformatics community thrives. Community thrives because of international collaboration and community support. In this spirit, any ideas, bug reports, and feature requests are absolutely welcome. Absolutely. Oh my god, I cannot spell. Yeah, I don't think that's very welcome. Please make your please create a new issue on our GitHub. Link that right there again. And we can just link to GitHub issues right there. And flag it. Actually, let's just create a new one and flag it with the appropriate. Oh my god. Tag. Okay. Anything else? Yeah, I think that's good. That's how I want this to be structured. Okay, we have installation. Yeah, I think that's very nice. What's the warning? Cannot resolve this path. Why not? Wait, maybe this should be like this instead. Yeah, okay, that fixed it. Nice. Oh, we have a bunch of spelling errors. The iGEM Munich 2025 Mesa Designer project is, yeah, a software package. Okay. Yikes. Yeah, okay, nice. I don't know comma stuff. What's the issue here? The official name of this software platform is spelled with a capital H. Really? Wait, GitHub is spelled with a capital H? Is it? Let's. Oh my god. Oh yeah, okay. So I guess both. Yeah, okay, sure, fine. GitHub. Fine. Nice. Now we have no complaints by the IDE. That works. Very nice. So yeah, this can also stay there. Remove that, and I think we can make this change. Contribute that. Give it that. Oh yeah, right. We don't need all of these pictures. We only need dark.png. updated README. We can push that. Now let's check GitHub. Nice. We've got the updated README up there. Perfect, perfect, perfect. Oh, publish Python application. Python package. We can create a workflow for this. Not right now. Okay, that does that fixes the README. Let's see. Are there other things right now? So we could write tests. Or some more functionality. Although right now I think the functionality itself is pretty fine. It's okay. We have absolutely everything that we have in the Mesa GUI application. However, of course we can add stuff. So maybe there's a type annotation that we can add. Sorry guys, I'm just thinking right now what I might want to do. I mean, maybe we can supply like an overview over these different parts. Although you can just get them because they're just part of the package, so you can just import them. Oh, the fret chains. The fret chains are still missing. Move component to annotated port. Length string. Yes. Create that. To fret chain. And what this will do is it will create a new Mesa chain, which has everything stripped except for the fret chains. So I think we can just say yeah. Chain Mesa chain equals self dot self, and then just for component in actually it's already set just because it's faster. The ones that we want are protease, PRS, cargo, and AIP. Protease, cargo, PRS, and AIP. Chain dot move component. Actually, it's that move statement right here. If component in self dot in chain dot parts dot keys, then we can remove this component. And then we return the new chain. Actually, sorry, incorrect. We need to create two chains. We can create a Mesa. Yes, this returns a Mesa assembly. Sorry about that. we need a chains, which is a Mesa assembly, which will just be a new Mesa assembly. And then we can say chain, Mesa chain is this thing. Pop those parts off, and then we say chains dot set chain. The name will be mvenus. And the Mesa chain is chain dot add Maybe we want to do a custom component thing. Def add component name string and sequence string, and this returns just itself. Yeah, I think that might be really cool, because then you can just add, you know, whatever. And that's the idea of the Python package, that you can do more than you could just with the tool. We have a value error if they have nothing there. Name cannot be none. If not sequence, value error, sequence cannot be none. In the end, we just return self. And then we do, I think this should be very easy, self.parts name equals a new annotated part with a sequence equal to sequence. And actually, let's give them the option of having also a part ID, which can be string or none, which is set to none. What else? We have name, part ID, and description, right? Yeah. Description can be of type string or none and is set to none. And an annotation of type string or none, which is also set to none. And then we do name equals name, part ID equals part ID if part ID, else just name, description same thing. If it exists, we want to add it. Otherwise, we just use the name again. And then for the annotations, the seek annotations, we can create a list of an annotation which has the name and I think that works. Oh, actually this says name if not annotation, else annotation. Good. Now I'm just thinking for a second here. If we will index this as name underscore custom part. And then down here, yes. Okay, what are you complaining about? Yeah, this needs that. What's the issue? Mesa chains, it's just none. Okay, set that to none. Add component. The name is going to be mvenus. And I don't think it's spelled that way. Let me check the data. So in the fret sequences, we have the ICDs. Well, yeah, no, that's not capitalized. So let's not do that either. Venus. Chain is this chain plus Venus component added. We can import this data. So fret ICDs. The sequence is from Fred ICDs, M Venus, and then 1. We don't need a part ID, we don't need a description or an annotation because this will all be annotated properly already. Okay. And then we can create a second chain, chains.setChain, cerulean, which is almost the same thing, except we do chain dot. Ah, wait, this will modify the original chain. Of course. Yep. Well, let's remove component Venus, and then we add a component cerulean, and the sequence is Fret ICDs cerulean, and the second part of that thing. Okay, and then we can just return chains. Perfect. Very nice. Very nice. Yeah. Now we can also do this stuff. We can remove some spaces there. That gives us the fret chain functionality. Now to fret chains. The whole Mesa assembly thing. I think it would make sense to have a function which can output like everything in a genbank string. So 2 genbank strings. This will return a list. Actually, it will return a dictionary of string and string. Just for each chain that was in the Mesa assembly, we create an entry and then yeah. Mesa chain or name cannot be done. Genbank strings is in a dictionary with actually this is just name and then Mesa chain dot to genbank string for name Mesa chain in self dot Mesa chains dot items, and we can just return this. Okay, yeah, that was very easy. Now for the file part, I don't think that a genbank file can contain more than one sequence, right? So this would have to be multiple chains. But now that we've got a bunch of new stuff going, I think next up is writing tests and doing all of that, and I don't like tests. I don't think most people like tests. I think most people don't like tests. So yeah, I'm gonna go grab something to drink, and I'll be right back. See you guys in a bit. back, guys, and we are back with some very healthy drinks. Let's see. So we're gonna now write some tests, test out this functionality. I'm currently, I'm just thinking right now. I'm thinking how exactly I want to do this. So I guess first of all, coverage. Let's just step through this entire thing and create one big component and see if it works. So, okay, coverage test. Coverage test. There we go. Yes. From Mesa Designer, we want to import. Actually, from Mesa Designer.mesa, we just import everything. That gives us everything, and then we have a few tests. So the first test is going to be, sorry, didn't mean to open that. The first test is going to be just creating chains. So def test Mesa chain. What's the issue? Yeah, okay, there's nothing here yet. Okay, nice. Chain A is a new Mesa chain, which requires no parameters. Okay. Does it just not take any? Oh, it doesn't. Okay, well, sure. I mean, yeah. Should a Mesa chain have a name? Maybe. Maybe not a bad thing to keep track of. But this is not required. Self.name is very, very easy right there. But you know, if you want it, you can do it. Chain B is going to take advantage of this, and it's going to be called B. That just creates those two. That's good. Okay, let's see. We've got this covered. We can run and get parts at the very end. I think we should definitely do that. Should we create a bunch of annotation, like annotate the parts, or actually, is that even supported right now? If I just want to add an annotated part, I don't think that's possible. Let's create that as functionality as well. Def add component, which takes a name and an annotated part of type annotated part, and it returns itself. So I'm actually unsure if you can. Let's call this add part. If name is none, raise a value error. Name cannot be none. If annotated part is none, we raise another value error. Annotated part cannot be none. And that should be an S right there. And then we just added self.parts with same thing here, name custom part equals the annotated part, or sorry, annotated part. Oh, and then we return self. Very nice. Let's just quickly split this up into two. and make that a bit wider. We've got some space on the stream left. Good. Right, we create the chains. Let's add some. I mean, yeah, let's just go through this from top to bottom. We add some binders. Chain a dot add binder. The sequence will be binder a sequence. Very creative right there. We don't need a name. We don't need anything. So we're not going to use anything. And then for chain B, we're adding another binder with sequence binder B sequence. Name is B binder. Annotation will be binder B annotation. Nice. Let's add some linkers. Chain A dot add TMD linker. Sequence is a linker. Oh, that's not going to work. Yeah, that's not going to work. Because, so, yeah, why is this not going to work? Because in GenBank you can't have these symbols. I want to test this, not, like, this is not going to be a real test. This is not going to be proper software tests. But instead, I'm just going to open this in Genius and see if that works. Instead of, actually, like, because you'd have to do so much validation, and I don't feel like that's necessary or practical. B linker with all the options again. Although, yeah, actually, let's just do this. That works fine. We need a protease sequence, sure. So chain A dot add. Oops. Chain A dot add protease. Let's rename that to just protease. And then this also. Add protease. The protease name for this one is going to be, oh god. So that's definitely something that could be useful. Getting, yeah, definitely useful if we could get this data right here, just from the package itself instead of, I mean, we could simply, it's imported, it is imported, but I would prefer to also give the user like an easier way to see it. End of data, yeah, and then duck keys 0. What's the issue here? Okay, convert that to a list and then get the first one. No, yeah, that's not how you convert it to a list. That's just a list of nothing. There you go. And then chain B will get a custom. Chain B dot add protease. Protease. Oh, custom protease, sorry. Custom protease. And the sequence is custom C protease. So like the C terminal end of this. Name can be C protease. And annotation. Oh, that I don't like this right here. Let's not do this. Let's put this in one line. The annotation will be C protease annotation. Okay, there we go. Nice. All right, we need a PRS. Chain A dot add PRS. The PRS name is going to be PRS. Fairly simple. And then chain B gets a custom one. Add custom PRS, which requires a sequence. Custom PRS. Name is custom B PRS. And then the annotation is custom B annotation. Yeah, I think you guys are seeing the pattern here. We just create everything. So we've added the PRS to both chains, so it makes sense to add the target to both as well. Chain A dot add target. Sequence will be chain A target. That's probably something we should do. Whenever there's a custom sequence entry, turn that into uppercase. Yep, we'll do that in a second. The name is chain A target, and the annotation is chain A annotation, a target annotation. There we go. All right. Let's just not give one to chain B. Yeah, let's just not. Let's see what happens. We also need a TMD. Add TMD. Right now we have a TMD linker, but no TMD, which works. Yeah, you can do that for intracellular MESA, but it's a very long linker like this. So actually, I want to see. We could, yeah, for this one we're gonna not give it a sequence. So yeah, let's create extracellular MESA on chain A, intracellular on chain B. Makes no sense, but for testing it works. Okay, sorry. The TMD that we're gonna add to chain A is going to be FGFR4. We don't need a custom TMD. We do want a signal peptide on chain A. Chain A dot add signal peptide, and the peptide name is just CD4. That works. We don't want an AIP on any of them. We don't need extra components. We don't need extra parts. We don't want to remove stuff right now. I mean, yes, we have to test all of this, of course, but I think it's fine. Let's create AAP is chain A.2 annotated part. Name is A annotated part. That's not how you spell that. Doesn't matter. It's fine. And then BAP is chain B.2 annotated part. Name is B annotated part. Let's get rid of this annotated part. Nice. Genbank string, fret chains. Yeah, let's just for a second here. So we're gonna save AAP dot save genbank file. We're gonna call this one AAP dot GB, and then we're gonna do chain B dot save genbank file. B chain dot GB. Actually, we're gonna save all of these because they should result at the in the same thing, right? Save genbank file bap.gb. Then we can just check if these are identical. And then also chain A. Save genbank file a chain.gb. Good. Yeah. we can do some assertions right here. Assert AAP dot to genbank string equals chain A dot to genbank string, and then the same thing for B as well, BAP. But this is not a great test. Because yeah, this is the same code, so if this is broken, then yeah. Okay, let's run this one. Ooh, it failed. Type error. Interesting. Let's go ahead and debug that. I think this error was right here. Okay. We go into this. We have a sequence, and this mesa chain has parts which have themselves sequences which are just strings. Okay. So we create this, we do this, we do this, we do this. Okay. Right now, component is signal peptide. So if we check out signal peptide, this has a sequence. Okay, that looks fine. And the seq annotations are empty. Okay. Step over that. Seq annotations now exist. And now let's step into this. The sequence is a string. So we can return this, and then oh, that works. Okay, so the error occurs later. Okay, nice. This is not any of these. I don't think it should do anything. Yes. The next component is tags. Ah, could this be an issue with tags? Because tags, well, first of all, tags aren't even in this. We have no tags. So we just skip it. Next is binder, which also just has regular sequence. Should not be a problem. That works. And we have a TMD linker, so this shouldn't happen. Okay. Next component is the TMD linker. We have the sequence right there. We can append the sequence, and we are not any of these, so we just skip it. Good. Next up is the TMD itself. Okay, the TMD is also just has a sequence. We do want to add this now. Okay. Then next up is fret. Right. Okay, I know fret is not in here. So we get to protease. Okay. Ah, interesting. And this is a list. So there's an issue with adding the protease. Yep. This should be that. And that should fix it. Okay. Guys, I will be right back. Let's just run this one more time. Another issue. Ah, yeah, this is a GenBank issue. Okay. So let's just name this that. Run that again. Assertion error. Interesting. Very interesting. But we have files now, so we can check this out in a sec. Okay, I'll be right back. See you in a moment. I'm just taking a short break. All right, and we are back. Yeah, so we're just now testing a few things, and apparently there are differences in the... Oh wait, yeah, this doesn't work. So this is actually something I don't know about Python. Does it... Which one of these checks? No, this one would be the correct one. But let's check out these GenBank files for a second. So if we open Genius Prime, which thanks to Genius, we were sponsored once again by them this year. So yep, thank you very much for that. It's a great tool. The wet lab people especially use it all the time, but also now with all this software, I have also been using it a lot. Let's show you some Genius. So yeah, Genius Prime is just a tool where you can manage your parts and your composite parts and everything, but all of this is like, yeah, our stuff that we've been working with this year, and you can have shared databases, and so it's a really, really cool tool. So let's check it out. So we have a... Yeah, this is not working. Okay, nice. But it looks like it's a general problem. Okay, let's see. Oh, okay, so there's some stuff majorly wrong with this. Okay. Let's see if we can figure out what's going on. I'm gonna delete all of these for now. Let's go back to the IDE and we'll create it in small parts and see where it goes wrong exactly. Okay, so first of all, adding a binder sequence. So let's just use one chain for now. We add the binder a sequence, and then we create a GenBank file from this. Delete this stuff over here. Where is it? Save the GenBank file. I'll just call this a.gb. And actually, we're not gonna... I don't want to run this as tests right now, so let's just call this something else. Let's create a new file here, yeah, really quickly. Mesa test. Sure. We import everything from mesadesigner.mesa, import everything. We can just copy this. And let's run the current file, which saves it here. Okay, let's see this file. Okay, that already doesn't work. Let's step through it with debug. Okay. we want to go into this one. We have a sequence, and this currently has nothing. Good. Okay. We then create an annotated part with the sequence name and the sequence annotations. And I think that's where something might be going wrong. Yes, we want to check out this annotation, which that didn't work. Nice. Let's see if it created correctly. Annotations, annotation 0. Okay, name, start, stop. Why is stop 6? Is there an issue with how this is created? What? Oh, ran the wrong file. Sorry. Step into this. Yep, that's fine. Step into this. Step into annotation. Oh, come on. No. Why can't I do this? Okay, there we go. We create a new annotation with no start, stop. Okay, oh yeah, well, that's just wrong. Why would stop be length of name? Yeah, that doesn't make much sense. Okay. that'll do it. Yeah. No. That needs to have a, yeah, okay. That explains it. So either the annotation already knows its sequence, or we just can't do it like this. We have to Yeah, let's add the sequence as well. Length of that sequence. And now we have to go back to Mesa and change a whole bunch of stuff. And I think we also have to change stuff here, I would assume. Okay, seems to be working fine. All right, let's close this for a second. Okay. There we have an issue. So the sequence, yeah, actually, yeah, I think this is fine. Because it should be pretty easy to fix all of these. We just have to add it everywhere. All annotations get this. Nope, not self sequence. Oh, I guess we're doing this. So proteases, protease name 1, and then sequence is sequence. Here, sequences PRS data, PRS name 1. sequence is sequence. Sequence is sequence. Same thing again. Deleted no, one second. Let's make those tabs the same distance. Okay, and I think we're fine. Let's see, let's run it again. We run this file. We should now have a new thing here. Delete this. Import that. Yeah, actually, yeah, that's correct. Nice. That is the binder sequence. Yeah. Okay, and it adds this linker. I don't know why. Or sorry, no, I know why, but I don't know if we actually want that. Another thing, right? We said we want to make all the wherever there is a sequence entry, we want to automatically capitalize that. So here, for example, if sequence does exist, sequence equals sequence dot upper. There's a sequence entry here. Sequence equals sequence dot upper. No, none here. Here. Oh, sequence. Also, yeah, guys, if you have suggestions or questions, please do always write those in the chat. I would love to answer them, and especially if you have suggestions, definitely share those. Just to be safe. I mean, this shouldn't ever happen, I think, but now it's not a problem. Okay. All right. One last thing over here. We save it to a GenBank file. And the name is Mesa Chain. Yeah, I don't like that. Let's turn the name. Actually, let's just expose it as a parameter. Name string or none is none. If they do add it, we can say this is name if name. Else we will take the last part of the file path. So file path dot split on this, and then take the last one of these. Now this should output a file called a.gb again, yes, but it should call the mesa chain something different. So if we put that in there, it's called a.gb. Okay, good, nice. Yeah, perfect. It still works. Except we're going to then do some more processing on this path. Where is it? Here we will now split this on period. And then take the second to last one. Okay. Right. Now let's see if we go back to the big test here, if this works. Oh, cancel, actually, let's not do this. We have it here, right? Yep. No. Oh yeah, we can undo all of this deletion stuff. Yep, perfect. Let's delete these asserts down here. We will check that in a bit, but for now, let's just run this file. Yeah, I mean, it's nice that the test passed. Okay, let's check out all of these files. Okay, we have a signal sequence, very good. We have the binder sequence. We have a linker CDS FGFR4 TMD, followed by a short linker, followed by an N-terminal protease of the TEF protease, followed by short linker, followed by PRS CDS, and the chain target. Yes. Nice. Very nice. And it also has the stopcode in the end. Perfect. Let's check out the other files. A chain. The binder sequence is not annotated. Why is the binder not annotated? Oh, wait, no, it's here. It's just shifted. Everything is shifted way too much. Why is that the case? Okay. So this is a chain.gb. Okay, let's step through this one. Go in this one. Okay. So step in there. Yes, first to the annotated part. What happened? It didn't. Okay, it didn't do it again. Step into it. Okay, we have a string. And the annotations. And then the first component is going to be the binder. No, sorry, signal peptide, yes. And this now has the signal peptide. That's looking good. And the annotations should contain one annotation, CD4 signal peptide of length 26. I think that could be correct. Yep, it's looking fine. Next up, we have the binder. Oh, I guess we're still on the signal peptide. Yep. Next up, we have the binder, though. We're called tags, but we don't have tags. This should append binder sequence and a new annotation, which goes from 52 to 67. Okay. So there's clearly something wrong with the shifting in the creation of the annotated part. Let's rerun it. Oh, sorry, that's incorrect. We want the coverage test. Debug this thing. Step into this, step into this. We can create this with the binder, or well, with the signal sequence. Then we have the tags, and then we have the binder. Okay. Alright, let's step into the annotations, sure. Shift annotation. The amount is 26. And currently self.start is already 26. Why is self.start 26? And then, yeah, this shifts it way too high. Okay, so I see where the problem is, but why is it not 0? I don't understand why the annotation is already that high. Does it come from add binder? But that doesn't... Oh, okay, yeah, okay. So, the problem is that if you do this, this modifies the original file, and this also modifies the original class. This shouldn't, or object, sorry. This shouldn't actually write it to the. I see the issue. Okay. Yeah, that makes sense. So this cannot. So it's shift annotation. I see. Yeah, because this writes it to the actual object, not. It doesn't create an entirely new object. Okay. So maybe that's actually something. Yeah, I don't know. If you have ideas on which functions should change the file and which functions shouldn't. That would be very welcome, because some of them obviously have to change the original class, the original object. Sorry, but I guess some shouldn't. So shift annotation. So yeah, I guess we need in place and non in place methods for all of this. Good question. What would be the best way to do this? I think it would make sense for the functions to change the object, and then just this function has to redo it. So essentially create an entirely new object and return that instead. So yeah, to annotate a part shouldn't change the original object, but these should. Yeah. So we need to create a new object to do this. Now I'm unsure, because in Python, if I just do that, it'll just give me the the pointer, right? Not a completely new object, if I'm not mistaken. So I guess we need to make sure that it doesn't just give me that. Yeah. Okay. So we need deep copy. Okay. um. Yeah. And then anywhere in here where it says self, we need temp. I mean, I guess for this part it wouldn't make a difference, but just to, keep it consistent. Also, this would make a multi-threaded implementation easier. Yeah, I think that's fine. Now, I think this exact same issue is down here as well. So okay, seems good. Let's run it again. Delete these files. Key. I'm going to show you Genius again. And then we can take a look at these new documents. All right, so these can all go in. Oh, did only copy the first one? Strange. There we go. Yeah, that's looking good. Okay, so that appears to have been the problem. That's the signal peptide, that's the binder, that's the linker, that's the TMD, short linker, N-terminal protease, and chain target, PRS. Yeah, that's all looking good. Nice. Now let's check out the B stuff, because B is obviously a bit different. Let's see if that worked too. Wait, did we only add this little stuff? So the binder is correct, binder sequence. We have blinker, which is correct. We have custom protease, custom C protease as the annotation. We have a short linker after that, and then we have a custom PRS, yeah, and no targets. Yep, okay, it's looking fine. Let's check the B chain. Yeah, that looks good. Now I wonder if that also solves the issues from earlier. So assert AAP dot to genbank string is the same thing as chain A dot to genbank string, and then this should be that. Let's see if this works. Run this test. No, it doesn't. Okay, interesting. Still different. Yeah. So that's the difference. The problem is that the order of the annotations is not the same. So if can we open these here? Yeah, perfect. And I think it's already complaining about the first one. Yep. So let's just take a look at those two. This file and this file. We compare them. Yeah, this is where they usualize. This is called a annotated part, and this is called a chain. So yeah, okay, that makes sense. Because of this name thing here. Okay, yeah, but that's fine. Otherwise, this looks good so far. So we definitely have to make an update to the Python package, and also we should push this to GitHub. But first, I want to see if we can test the rest of the stuff as well, because there is some more. There are some more things that we've tested. This we look at this, the fret chains, right? Yeah, let's test the fret chains. Get rid of this part. So if we take a look at the fret chains, the way this is supposed to work is you create a new Mesa assembly, and then we could turn the Mesa assembly into genbank strings. So let's actually at this point create a second function here, save genbank files, which you will give this a file path to a dictionary, and then it'll save it for like every name. It'll create a new file in that dictionary. Sorry, not dictionary, a directory. Sorry. It doesn't return anything. We can say for chain in self.mesa chains, chain dot oh, sorry, yeah. Name chain in mesa chains dot items. Chain dot save to genbank file. The file path can be file path plus this plus name plus .gb. That should, I think that's good. Okay, so we can go into the coverage test again, and we can say, let's just say chain A dot to fret chains, which will give us a Mesa assembly. So fret assembly, Mesa assembly is a chain A dot to fret chains, and then we can say fret assembly dot. What's the issue here? Oh, does fret chains not have an annotation? What are you talking about? Okay, it was just wrong. Nice. Dot save genbank files. The file path can be just this. I don't know what it's complaining about. Why are you considering this an untyped function? Do you want me to type self? What? No way, right? Let's just run, maybe it'll error. And we're back to debugging again. Sorry. Create the Mesa assembly. Create this. We have these components. If they are in there, we remove them. Ah, yes. This is an issue. Because this actually removes it. We don't want that. We want this to create a new chain. Chain Mesa chain as copy dot deep copy self. That's what I was talking about earlier, where I said there's probably another error like this. But yep, I couldn't find it. So yep, that was that. Right, we now have a new chain here. Remove these parts. Okay. And then we say chains.set chain. Add this. Let's check out chains. Actually, I mean chain should have this part too, right? MVenus custom part. Oh, because it's not called MVenus, it's called MVenus custom part. Yeah, I don't know if I like that. Let's not append this, because that will just be confusing to people. This name should be consistent throughout adding and removing custom components. So let's make that key just name. That makes more sense. I think that's far more intuitive. Still have another error. Okay, yeah. Component not in Mesa chain. Okay, so that was not the only issue. Remove this stuff. We add this. Let's check out the chain. Why is it still there? MVenus custom part. Wait a minute, what did I just change? Ah, I see. There are two parts where this exists. Let's run this again. There we go. Nice. And we now have mcerulean and mvenus.gb, which does not work. Okay. It removed it, didn't add it. No, why did it not add it? Let's check out this part. So the fret assembly has two chains, which Venus has parts, which includes... Well, that's just wrong. But okay. Interesting. Is it that it... Oh, because this is, again, same issue. We can do a copy.deep copy of the chain, because we have to do it anyway. Like this. We add the component to this, then we don't have to remove it from this one. We can just add it. Now let's re-debug this. Okay, if we look at the fret assembly now, we have Mesa chains, we have Venus parts, which now has Venus as a part, okay, and this also seems to be correct. Cerulean part, cerulean, and sequence. Okay, yeah, that's looking good. And yeah, don't worry, these look very similar, but there are some minute differences between the two sequences. Fret imaging is actually a pretty cool technology. Alright, we do this for every single one. We save the GenBank file, annotated part, we do the temp deep copy, and then, okay, component is signal peptide, sure. Step through this, tags, binder, we add the binder to the sequence. We add the TMD to the sequence. We don't have fret. I see. So, yep, okay. The issue with this is simply that this should index it to, or we'll use this key, not anything else. So we just save that as fret. Now if we run it, it probably works, hopefully. Okay, it definitely created stuff. Let's check out these files again. Have I been showing you Genius the entire time? Oh, I'm so sorry about that. Keep them separate, and it didn't work. Nice. Let's go through it again. This is deep copied. We want to step through until this says fret. TMD. Okay, so let's check out this temp part. It has parts and it doesn't have fret. Why does it not have fret? It's interesting. Oh no, this is incorrect. Yes, this should be cerulean and Venus. And the component, this should be fret. Oops. Yes. that makes sense. That's fine. Okay, now if we run it, maybe it'll work. File, run this. Sorry about that. Replace these, create list. Oh no, that's not what I wanted. Anyway, it worked. There's one tiny thing I want to change there. It's supposed to, of course, annotate them with the correct sequences, and not with fret. So let's just create that in the I wonder if that's already in the fret assembly. Yep, probably is. If we create these, we add the component, and since we have control over this, we can just give this a annotation of mVenus, and this can get an annotation of mcerulean. That's the wrong thing. We want to run this one. Check out these files, keep them separate. Perfect. Nice. Yeah, okay. So as you can see, this works now. It has been 2.5 hours, and so I think we will be... Yeah, we're gonna finish this stream now. If you're interested, we will see you again later, and if not, then perhaps tomorrow, where we will finish up some more of this package, and we can then finally go on to writing documentation and creating some more videos about, you know, how to use this stuff, using it, expanding it, how is it structured, all that fun stuff. And then finally on Thursday we can move on to dry lab modeling, stuff that we did during iGEM. I think that's going to be interesting because we learned a lot of stuff in the few months that we had to work on this, and I think there's a lot of valuable advice that we can definitely give to future teams, or to you if you're just interested in learning more about modeling of proteins, some protein optimization also. There's some really interesting things. I don't know if you missed it, but you know, you can split proteins and then they can reconstitute to form the original structure and still function. I think that's very interesting. That's what we're going to be looking at. For now, I'm just going to commit this, and I guess this is just fixed issues, and included some functionality. Yeah, really helpful commit message functionality. Here we go. We can quickly